Hello and welcome to lecture 27 of the course Theory of Computation. Right. So we completed chapters 1 and 2, which talked about regular languages and context-free languages. In this lecture, we will start with Turing machines. Okay. So we saw regular languages and context-free languages. So regular languages used like we saw the machine models like deterministic finite automaton and non-deterministic finite automaton. In context-free languages, we saw push-in automaton. In chapter 3, we see Turing machines, right? So which is actually an abstraction of the modern day computers, right? So this will be, as we will see, this will be more powerful than the models that we have seen so far. And so this is the beginning of the computability theory part, right? So at the beginning of the course, you may recall that I had promised that the goal of the course is to understand computation and to see what can be computed and what cannot be computed, right? Surprising as it may seem, there are things that even computers cannot do, right? Which we think is quite powerful and can do all sorts of computations. There are computations that even or there are questions that even computers cannot answer, right? Even if you give them all the information and all the time in the world, right? So let us see how the Turing machines are how they differ from the automata that we have seen so far, right? So they differ in 3-4 important aspects which I have listed down here. So one is that so like in many other cases, we have a state control and a tape which contains the input. So if you recall in DFAs, NFAs, PDAs, etc., the input, just one symbol is read in each step, or sometimes there is an epsilon transition, but it is just the input is just read, right? And at the end, if we are at an accepting state, we accept. If we are not at an accepting state, we do not accept. So the first difference is that we have a read and write head. Okay, so there is an input which is given in some tape, and the head can read as well as write. So when you read the input, it can also write something onto the tape. It could overwrite the contents of the tape. It could erase the contents and write something there. So the first difference is that we have a read-write head. The second difference is that in PDAs and NFAs and DFAs, we just read the input symbols one by one till we reach the end, right? And then that is it. If we were in an accepting state at the end, we accept. Here, the head could move left or right, right? So the head could actually, so there was no concept of the head moving to the left and right in the DFA or in PDA, right? So in Turing machines, the head could go to the left or to the right. It could take any trajectory based on how the Turing machine is programmed. The next thing is that we have an infinite tape. So in DFAs, NFAs, etc., we had just the input given, and that was it. There was no notion of extra space or anything. Here we have an infinite tape, and a tape that extends to infinity on one side. Right. So usually, so there are different models where we have which extends to infinity on both directions, etc. But this is the first model that we will see, and we'll stick with this model for most of the time, right? So the left side is bounded, and the right side extends to infinity. And finally, we had accept states in DFAs and NFAs and PDAs. So it was like this, we do the processing, you may be jumping across many states, you may go to the accept state, but maybe there is more string remaining, and at the end, so what really mattered is at the end of processing the string where we are, or right. So if at the end of the processing the string, if we are in an accepting state, we would accept that string, right? It doesn't matter if in any intermediate state we happen to move to an accepting state. Right? It doesn't matter. All that counts is whether we are at an accepting state at the end of processing, right? However, in Turing machines, there is a difference. We have special accept reject states which immediately come into effect. Meaning, if you ever move to an accept state, that's it, the computation is over and we have accepted the input. If you move to a reject state, that's it. The computation is over and we reject the input. Right. So these are the 3-4 distinctions that we have in Turing machines. Right. So at the end of the previous lecture, we mentioned this language, W hash W, where W is a binary string, and we said that it is not a CFL. So now let us try to see how a Turing machine can recognize this string. So what the Turing machine will do is the following, right? So I have written the string here. So one string is 01100 hash 01100, and as you can see, this string is in the language because it's W is 01100 hash followed by the same string, and these things over here, right? These things over here are blank symbols because there is an infinite tape after where we have the string. It's entirely blank symbols, right? But that doesn't matter. It's like blank symbols which are not which are distinct from the inputs. So how let's see how a Turing machine might try to see whether this is part of the language that it has to recognize. Okay. So what it will do is it will start from the left side, right, and see the first symbol in the left side. So the first symbol in the left side is a 0, right? So it can strike off the 0. So what do I mean by strike off the 0? So it can replace the 0 with some symbol, let's say like this, a 0 with a strike off, or it can replace it with an X or something like that, right? So when I say strike off, it means like it has to replace it with something which says that it has already been read, and then the Turing machine has to remember that it has struck off a 0, and then it starts moving to the right side. Slowly it starts moving to the right side, and it will keep moving till it encounters the hash symbol, right? So the hash symbol is this. So once it reaches the hash symbol, it remembers that it had struck off a 0. Then it sees the next symbol. So the next symbol is 0, and the struck off symbol also was 0. So now it strikes this 0 off also, and it continues. So now it comes back to the left side. Now from the left side, it checks for the first symbol which is not struck off, and the first symbol that is not struck off is 1. So now it strikes off 1. It remembers that it has struck off 1, and then it keeps going to the right side till it encounters the hash symbol. Once it reaches the hash symbol, it now starts checking for the next symbols, and it sees a 0, it sees something that was struck off, and the next symbol that is not struck off is a 1. So again it strikes off this 1. So and basically the first two symbols 0 1 and the 0 1 after the hash has been kind of matched. Now it comes back to the left side. The first symbol that is not struck off is 1. It crosses the hash. The first symbol that is not struck off is 1. So things are fine. It comes back. The first symbol that is not struck off is 0. First symbol that was not struck off is 0. Fine, right? Suppose it happens so that the symbol that we have here was a 1, right? So now it will come to the left. The first symbol that is not struck off is a 0. It remembers that it struck off a 0. The first symbol that is not struck off on the right side of the hash is a 1, right? So now it knows that the symbol that it struck off in the left side was 0, and the symbol that we are seeing now is a 1. So we know it is not equal. So then it will be rejecting this, right? So it knows it's not the same. And it, for that matter, it did not wait up to right. So now if it is indeed a 0, then it'll check whether it is a 0 on the left side and check whether it is 0 on the right side and strike off. And then it will come back to the left and see whether there is any symbol to the right that is not struck off, and it sees that everything is struck off till the hash. So the first symbol that it sees from the left side that is not struck off is a hash, and then it goes to the right side and sees if there is any leftover symbols that is not struck off. So suppose there was there was a symbol here, let's say 0. So that means that the symbol to the left, the string to the left of the hash is not the same as string to the right of the hash. So this means this will get rejected because there is something to the left of the hash. Suppose there was no 0 here and if it was just blank, in which case it will get accepted because everything to the left is struck off and it matched with everything to the right, and everything to the right is also struck off. But if we had some other things, like let's say if we had 0110 hash 01100, this will not be accepted because it will strike off 0011 1100, but then it will see a 0 that is left, not struck off. And same thing if it found something like, just give me a moment, if it found something like let's say 01101 hash 0110, right? Suppose this is the entire string. Again it will strike off 0 and 0, 1 and 1, again 1 and 1, 0 and 0, and then it will strike off this 1, right, the last one in the left side. But then when it comes to the right side, there is nothing to match it with. So even in this case it will get rejected. So these two will get rejected. And even simpler strings like let's say 01100, sorry, I'll just write it, 01100 hash, let's say 00100. So even this will get rejected because the first 0 will get struck off with this. This 1, the second symbol 1 will not get struck off because the second symbol after the hash is a 0 which does not match. So this will also get rejected. So this is how a Turing machine may operate on a language like this. So if the Turing machine is trying to identify that language, this is what it has to do. And the same thing I have written in a bit of detail. So what does it do? It strikes off the first position from the left side, which is not already struck off. It remembers a symbol that was struck off, move to the right, go past the hash symbol, and cross check with the first symbol in the right of the hash that is not struck off. If it is not the same, then reject, else it continues or repeats. If no symbol is, suppose it struck off something in the left, but there is no symbol to the right side, then it rejects. Suppose it strikes off something in the left, but there is no hash symbol at all, right? If there is not even a hash symbol, then it's not even of this form. Even then you reject, right? Now finally, if all the symbols to the left side has been struck off, and see if and it has matched with whatever is struck off from the right side, it is still possible that it's not in the language because there could be extra symbols on the right side. So check if there are extra symbols. If there are extra symbols, you reject. If there are no extra symbols, it means whatever was struck off from the left matched with whatever was there in the right. In that case, you accept. Right? So this is the kind of intricate details on how a Turing machine may operate. And we can even define. We can formally define the Turing machine, and all of this, like we saw the transition function in DFAs and NFAs, right? We can define a transition function for the Turing machines as well, and so that these kind of rules. So here I have written the proceedings, right, or the way the Turing machine has to operate in English, right? But this is kind of high level, and we can encode that into the rules of the transition function in a bit of detail. But that is kind of extremely intricate and cumbersome to do. The point is that almost anything that we want to do like this, like where we give instructions, can be accomplished, right? So we will not get into those kind of details, right? We will not get into those minute details as to how we accomplish these rules in a Turing machine. We will just give high level descriptions such as this, right? So the details are tedious. The main point that I want you to know is that all of this can be accomplished. So one small question at this stage: Suppose we want to recognize this language WW. So it's the same as this, same as D here, but there is no hash symbol. So it does not, like in our algorithm here, we try to go past the hash and then look for the hash, etc. If there is no hash, how will it recognize this? How can a TM recognize this? So basically it has to identify the midpoint. How will it identify the midpoint? So this is one thing that you can think about. Perhaps it can do some kind of accounting or something like that, right? So this is something that that I want you to think about. So what it can do is so one is that it can use a counter of some sort. It can count how many symbols are there overall, and then it can identify which should be the midpoint. If the count is an odd number, then we know that it is not of this form, because WW means a string is repeating, so the length is uneven. Otherwise, if the length is even, then you know let's say it's of length 20, then we know that the symbol, the point after the 10th symbol is the midpoint. And then we can, once we identify the midpoint, it's pretty much the same, right? So formal definition of the Turing machine, right? So this is in fact a deterministic Turing machine. So there are many variants of the Turing machine that we will see. This is a deterministic Turing machine. And again, I am not writing the definition in full detail, but just the main parts that I want you to focus on. So Turing machine is a 7 tuple, okay? Q, sigma, gamma, Q, sigma, gamma. Then delta is a transition function. Then Q0, which is the start state. Then Q accept, which is the single accepting state. Again, we don't have multiple accepting states. We just, when we have to accept, you just move to the accepting state. Then Q reject, which is a single reject state. Q, sigma, gamma are finite sets. Q is a set of states. Sigma is the input alphabet. Input alphabet means the strings that are recognized, strings that are computed or processed in the Turing machine. What are they comprising of? Sigma. And gamma is the tape alphabet. So in the tape, we may use more symbols than what is. So everything that is in the input alphabet has to be in the tape alphabet, but there could be other symbols in the tape alphabet. Q, sigma, gamma are finite sets such that sigma is a subset of gamma, right? Because input alphabet, all the input we should be able to write on the tape, and this blank symbol is part of the tape alphabet. So this is blank symbol, which is used to denote that a tape location is empty, and blank symbol is not part of the input alphabet. We cannot have a blank as an input symbol. Then Q accept and Q reject have to be distinct, right? So because both of them are different, and this is how the transition is defined. So the input, so again, it's a deterministic Turing machine. So it's a function. If you are at a certain state Q and you read something from the tape in gamma, right? Then we go to another state. You write something onto the tape, something like PDA, because in PDA also you can read the input and the stack, but here there is no two input and stack, there is only one input, there is no stack. But you could also write onto the stack. So like that, you could also write onto the tape. And then LR, which denotes left or right. So this indicates how the head should move. The head could move left or right. So suppose you are in state Q4 and let's say this is the input tape. This is the input tape. Like 0, 2, 3, 1, and it's currently the head is pointing at 3. Okay. Suppose we have the rule delta of Q43 is Q60R. In that case, what happens is, maybe I'll use a different color. In that case, what happens is 0 remains as it is, 2 remains as it is. So the 3 is replaced by 0. So it reads as 3 and replaced by 0. and then the next cell is 1, that is all the same, and the tape head moves to the right, so which means the tape head is to the right, and the state is Q6. So if the rule delta Q43 was to write 0, move right, and then go to state Q6, then this would be the next situation. If instead the rule was this, which means to go to state Q10, write 1 and move left, then it would have been 0, 2, 1, 1, and Q10, and you move left, so you were pointing to the third location at the number 3. Now you move left, and you write 1 here, which is written here. This 1 is new, and then you move to the left, and you are at state Q10. So suppose the transition rule was delta Q43 goes to Q10, write 1 and move left, then this is how the Turing machine tape will move. So this is how we define the transitions, right? And how does a Turing machine? So again, as I said, we can, whatever we mentioned here, right? Strike off the first position and then go to the hash and then go to the right side and see if this is same, etc. All these things can be accomplished by states, but states and transitions. But we will usually not be getting into that kind of detail because it's getting too cumbersome and difficult to manage that. Okay, so some more things. So at the beginning of computation, let's say you want to, just like you give an input to the DFA or an NFA, you want to give something as an input to the Turing machine, right? So then you keep the input in the left side of the Turing machine. So suppose the input is 0011, right? So then you write 0011 on the tape followed by blanks. So the rest of the tape is empty, right? And the head points to the leftmost location, and you are at the starting state, which is Q0. And then it may read, it may write, it may move to the left or right or whatever, and then it will till it goes to an accept or a reject based on the transition rules, right? So delta does all this, and as I said, computation starts from the leftmost end of the tape, and one small point, so here we explained from this point 0, if it tries to move right, you go here, if it go left, we go here. But if we try to go left from the leftmost location, we just remain there because we cannot, there is nothing more to the left side. And like I said before, the computations end when you reach the accept or reject state. But it is also possible that neither state is reached, neither accept nor reject. This is called an infinite loop situation. So just like in a computer program, you could have an infinite loop which you can never come out of. Like that, even in a Turing machine, you may end up in a situation where you just are doing something again and again or something repeatedly without ever going to an accept or reject. So there are three possible ways a Turing machine computation may proceed. One is that it accepts and ends. Another one is that it rejects and ends. Third one is that it neither accepts nor rejects. It could just continues computation forever. So this is called looping, right? Because like an infinite loop, right? And accept and reject are called halt, because once you reach accept or reject, you stop the computation and you end, right? So the next thing is a definition called configuration. So suppose there is a Turing machine and suppose it has some rules, but I am computing and I reached a certain point of computation. Now I just want to tell you where I have reached so that you can resume the computation. Right? So what are the information that I have to give you so that you can continue the computation, right? So I cannot tell you the input because I don't want you to start from the beginning. But now the tape contents may have changed. I may have overwritten on the input. I may have reached some other symbols. I may have written over things multiple times. So it will be simplest if I transfer the contents of the tape to you. Not just that, I should also tell you which state I am in and which position of the tape the head is pointing to. So if I can tell you these things, then you can continue from wherever I have stopped. Okay, so the configuration contains of exactly this information. It contains the state, the head position and the tape contents. So once I tell you all these three, you can continue the computation from this point. Right. So in this picture over here, the state is Qi, head position is 4th, right? It's pointing to the 4th symbol, and the tape contents is 10 10 11 followed by blanks. Once I tell you this, you can start computation from this particular point and then see where it goes. It doesn't matter how I reached here, right? So these three pieces of information together are called configuration: state, head position and tape contents. Maybe I will just put a box. Okay, so these three things are called configuration, and this is basically the information that I need to give you so that you can resume the computation. And it is usually sometimes we denote configuration in this kind of notation. Basically, we write the state in between the input string. So we know 101011 is the input. So I write the state in between. So Qi is the state. I write it in the 4th position. This denotes that Qi is the state and the head is pointing to the 4th location. Okay. So this is one way to denote the configuration. Instead of telling state Qi, head position 4th and tape contents 101011, I can just give this string in which the state is inserted into the 4th position. So then you know the state, you know the head position, and also the rest of it gives you the tape content. Okay. So we say that a configuration C1 yields a configuration C2 if from the configuration C1 you apply the transition rule and go to C2, right? So suppose you have this configuration U, A, Qi, B, V, which means you have U, you have A, right? You have B, you have V, and Qi is the state and you are pointing at the location of B. Now suppose the rule is that if you are in state Qi and you are reading B from the tape, then you have to write C, you have to go to state Qj and move left. Suppose this was the rule. If you are in Qi and you are reading B, you have to move to the left, go to state Qj and write C, right? Suppose this was the transition function, then from this configuration we will move to this configuration, right? So where B is overwritten by C, right, and you move left and the state is Qj instead of Qi, right? So B is changed into C and the tape head has moved one step to the left. So we can say that U, A, Qi, B, V, this configuration, which is what is given here. So this is U, A, Qi, B, V, yields U, Qj, A, C, V. So notice that the state in the configuration came one step to the left because the head has moved one step. So here U and V are some strings and A, B, C are single symbols of the tape alphabet. Now one question, suppose instead of if the rule was instead of QIB, delta QIB gives QJCL, if it gave QJCR, right, then everything would have been the same. But yeah, this is what I've written here. Instead of delta QIB being QJCL, if it was QJCR, right, so this L became R, everything would be the same. It would overwrite it with C, it would enter state QJ, but instead of pointing at A, it would point at the first symbol of V, this place. So that I have depicted here. If the rule was delta QIB is QJCR, then this would be the configuration UAC QJB, right. So we say that a configuration C1 yields C2 if C2 is the successor configuration of the configuration C1. And notice that we are in deterministic Turing machines, right? There is no non-determinism. So given this particular situation, right? So when I said this particular situation, the next step is clearly defined, right? So we know that UAQIBV, we know that this yields UQJACV, right? And that is a unique configuration that it can yield. In a deterministic Turing machine, there is only one clear configuration that it yields, right? So we say this. Now finally, maybe I'll just conclude by saying, when does a Turing machine accept a string, right? We say that Turing machine accepts a string by a series of, if there are a series of configurations such that, so this sort of thing we have seen in DFAs, NFAs, PDAs, etc. So the starting should be proper, ending should be proper, and all the in between steps should be proper, right? So C1, we say that Turing machine accepts W if C1 is a starting configuration. Starting configuration means the entire input string should be in the input tape and we should be at the starting state. So the input starting configuration is Q0W. I think we mentioned this earlier, right? So here we had mentioned it. If the input was 0011 and Q0 is the starting state, it should, the head should point to the leftmost and the input should be the only thing in the tape. So C1 should be the start configuration, and for all these pairs C1, C2, C2, C3, etc., we want C1 to yield C2, C2 to yield C3, and so on. So this should be a valid sequence of configuration so that they are all valid successors of each other. Ci should yield Ci plus 1 for all I, and finally Ck should be an accepting configuration. What do I mean by accepting configuration? It's a configuration which has an accepting state. So the state, so every configuration contains a state, right? So the state in the configuration Ck should be the accepting state. So once we have these three, you start correctly, all your moves are proper, and end with an accepting state, then the string is accepted. And the language recognized by the Turing machine M, like before it we denoted LM, it is a set of all strings which are accepted by the Turing machine, right? So once again, Turing machine accepts a string if it starts with the starting configuration, which is the starting state in the and the starting state being the state and the input string in the input tape, and the starting config, that is the start configuration, and for each of the C2, C3, etc. are valid successors of the previous one, and finally Ck is an accepting configuration. And the language recognized by the Turing machine is a set of all strings that are accepted by the Turing machine, right? So that's it as far as this lecture is concerned. So we defined what is Turing machine, right? And in fact, what we saw is a deterministic Turing machine. So we'll see many variants, right? So we'll see non-deterministic Turing machine, we'll see Turing machine with multiple tapes, etc. But right now, what we saw is deterministic Turing machine, and we saw the distinctions with respect to PDAs, NFAs, etc. Right? It has read-write head, which can move left or right. We have infinite tape and special accept reject states. We saw what is a configuration. We saw a formal definition. We saw what is a configuration. It contains three things: state, head position, and the tape contents. We saw this notation to denote the configuration, which is the input, which is the tape content where the state is inserted in the head position. And we saw the conditions for a string to be accepted in a Turing machine. So this computation has to continue. Initially, you start with the input in the tape and the head to the leftmost point and the start state, and then you just let it run. If it reaches accept state, it accepts. If it reaches reject state, it rejects. And if it does not reach neither, it does not accept or reject, but it just continues. It's a loop. And the set of all strings that are accepted is called the language recognized by the Turing machine. And that completes this lecture, lecture 27. That also completes week 5 lectures. So in week 5, we saw the equivalence of PDAs and context-free grammars. We saw pumping lemma for context-free languages. And we saw the beginning of introduction to computability theory, which is the definition of Turing machine. And we'll see more about computability theory and Turing machines in the upcoming week, which is week 6. And so see you in week 6. Thank you.